Hello everyone, welcome back to the CSE Guy. Today we are diving into some advanced topics in machine learning, focusing on ensemble methods like bagging and boosting, as well as various clustering techniques. We will explore random forest, gradient boosting, k-means, k-medoids, hierarchical clustering, and more. So let's get started. First, let's compare and contrast bagging and boosting in ensemble methods. Bagging or bootstrap aggregating is a technique that aims to reduce variance by training multiple models independently on different subsets of the training data. Each model is trained on a random sample of the data and the predictions are combined usually by averaging or voting. A classic example of bagging is the random forest algorithm, where multiple decision trees are trained on different subsets of the data. Boosting, on the other hand, is a sequential technique that aims to reduce bias and variance. In boosting, methods are trained one after the other, with each new model focusing on the errors made by the previous ones. The final prediction is a weighted sum of the predictions from all models. An example of boosting is the AdaptBoost algorithm, which adjusts the weights of incorrectly classified instances to improve the model's performance. So what are the key differences? Training process. Bagging trains models independently while boosting trains them sequentially. Second, focus. Bagging reduces variance while boosting reduces bias and variance. Third, model combination. Bagging combines predictions by averaging or voting while boosting combines them through weighted sums. In summary, both methods enhance model performance, but they do so in different ways and are suited for different types of problems. Next, let's explain the working mechanism of random forest and discuss its advantages and limitations. Random forest is an ensemble training method that combines multiple decision trees to improve classification or regression tasks. Here is how it works. First, bootstrap sampling. Random forest creates multiple subsets of the training data using bootstrapping, which involves sampling with replacement. Second, tree construction. For each subset, a decision tree is constructed. However, when splitting nodes, only a random subset of features is considered, which adds diversity among the trees. Third, aggregation. For classification tasks, the final prediction is made by majority voting among the trees. For regression tasks, it is the average of the predictions. So what are the advantages? First, robustness. Random forest is less prone to overfitting compared to individual decision trees. Second, feature importance. It provides insights into feature importance, helping to identify which features contribute most to the predictions. Third, versatility. It can handle both classification and regression tasks effectively. Limitations. First, complexity. Random forest models can be complex and less interpretable than single decision trees. Second, computationally intensive. Training multiple trees can be resource intensive, especially with large datasets. Overall, random forest is a powerful tool in the machine learning toolkit, particularly for tasks where interpretability is less crucial. Now let's describe gradient boosting in detail and how it improves model performance iteratively. Gradient boosting is an ensemble technique that builds models sequentially where each new model attempts to correct the errors made by the previous ones. Here is how it works. First, initialization. Start with a base model, often a simple one like predicting the mean of the target variable. Second, calculate residuals. For each iteration, calculate the residuals, which are the differences between the actual values and the predictions of the current model. Third, fit a new model. Train a new model to predict these residuals. This model focuses on the errors made by the previous model. Fourth, update predictions. Update the predictions by adding the predictions from the new model scaled by a learning rate to control the contribution of each model. Fifth, repeat. This process is repeated for a specified number of iterations or until the model performance stops improving. Improvement. By focusing on the errors of previous models, gradient boosting iteratively improves the overall model performance, often leading to high accuracy. Gradient boosting is widely used in various applications, including Kaggle competitions, due to its effectiveness in handling complex datasets. Next, let's discuss the k-means clustering method, including its steps, distance metrics used, and its strengths and weaknesses. K-means clustering is a popular unsupervised learning algorithm used to partition a dataset into k distinct clusters. Here is how it works. First, initialization. Choose k initial centroids randomly from the dataset. Second, assignment. Assign each data point to the nearest centroid based on a distance metric, typically Euclidean distance. Third, update. Recalculate the centroids by taking the mean of all data points assigned to each cluster. Fourth, repeat. Repeat the assignment and update steps until the centroids no longer change significantly or a maximum number of iterations is reached. Distance metrics. The most common metric used in k-means is Euclidean distance, but other metrics like Manhattan distance can also be used depending on the nature of the data. Strengths. Simplicity. First, simplicity. K-means is easy to implement and understand. Second, efficiency. It is computationally efficient, especially for large datasets. What are the weaknesses? First, choosing k. The need to specify the number of clusters k in advance can be a limitation. Second, sensitivity to initialization. The final clusters can depend on the initial placement of centroids, leading to different results on different runs. Third, assume spherical clusters. K-means assumes that clusters are spherical and equally sized, which may not be the case in real-world data. In summary, K-means is a widely used clustering method that is effective for many applications but has its limitations. Now let's compare k-medioids and with k-means clustering and explain situations where k-medioids may be preferred. K-medioids is similar to k-means, but instead of using the mean of the data points to represent a cluster, it uses the most centrally located data point known as the medioid. Key differences: centroid versus medioid. K-means uses the mean, which can be influenced by outliers, while k-medioids uses actual data points, making it more robust to noise and outliers. Distance metric. K-medioids can use any distance metric, while k-means typically uses Euclidean distance. So when we should prefer k-medioids? First, presence of outliers. If the dataset contains outliers, k-medioids is preferred as it is less sensitive to them. Second, non-Euclidean distance. When the data does not conform to the assumptions of k-means, such as when using non-Euclidean distance metrics, k-medioids can be a better choice. In summary, k-medioids is a robust alternative to k-means, particularly in datasets with outliers or when using different distance metrics. Next, let's explain hierarchical clustering and discuss the differences between agglomerative and divisive methods with examples. Hierarchical clustering. It creates a tree-like structure of clusters known as a dendrogram, which shows the relationships between clusters at various levels of granularity. Agglomerative method. This is a bottom-up approach where each data point starts as its own cluster. Clusters are iteratively merged based on a distance metric until a single cluster is formed or a desired number of clusters is reached. Example: starting with individual points, the two closest points are merged into a cluster, and this process continues until all points are clustered. Divisive method. This is a top-down approach where all data points start in a single cluster, which is then recursively split into smaller clusters. Example: starting with all points in one cluster, the algorithm identifies the most dissimilar point and splits it off, continuing this process until each point is its own cluster. In summary, hierarchical clustering provides a comprehensive view of the data structure, allowing for flexible cluster selection based on the dendrogram. Now, let's discuss the role of distance measures in clustering and how they impact the clustering results. Distance measures are crucial in clustering as they determine how similarity or dissimilarity between data points is quantified. Common distance measures include Euclidean distance, Manhattan distance, and cosine similarity. Euclidean distance measures the straight line distance between two points in Euclidean space. It works well for spherical clusters but can be sensitive to outliers. Manhattan distance measures the distance between points in a grid-like path. It is less sensitive to outliers and can be more appropriate for high-dimensional data. Third, cosine similarity. It measures the cosine of the angle between two vectors, often used in text clustering. It is useful for high-dimensional sparse data. The choice of distance measure can significantly affect the clustering results. For instance, using Euclidean distance may lead to different cluster formations compared to Manhattan distance, especially in datasets with varying scales or outliers. Therefore, selecting an appropriate distance measure is essential for achieving meaningful clustering outcomes. Next, let's provide an overview of the BITS algorithm and explain how it handles large datasets. BITS, which stands for Balanced Iterative Reducing and Clustering Using Hierarchies, is designed for clustering large datasets efficiently. It works by incrementally building a tree structure called the clustering feature tree (CFT). So how it works? First, clustering feature tree. BITS constructs a tree where each node represents a cluster and stores summary information about the data points, such as the number of points, the linear sum, and the squared sum of the points. Second, incremental clustering. As new data points are added, BITS updates the tree by either adding them to existing clusters or creating new clusters if necessary. Third, final clustering. After the tree is built, a secondary clustering algorithm like k-means can be applied to the leaf nodes to refine the clusters. So what are the advantages? First, scalability. BITS is efficient for large data sets as it reduces the number of data points that need to be processed by summarizing them in the tree structure. Second, memory efficiency. It requires less memory compared to other clustering algorithms since it does not store all data points explicitly. In summary, BITS is a powerful algorithm for clustering large data sets, making it suitable for applications where scalability is a concern. Now let's explain how the Chameleon clustering method works and its advantages over traditional clustering method. Chameleon is a hierarchical clustering algorithm that dynamically adapts to the shape and size of the clusters. It combines both partitioning and hierarchical approaches to achieve better clustering results. So how it works? First, initial clustering. Chameleon starts with partitioning the dataset into small clusters using a traditional clustering method like k-means. Second, dynamic merging. It then evaluates the clusters based on two main criteria: the interconnectivity of clusters and their relative closeness. Clusters that are well connected and close to each other are merged. Third, final clustering. This process continues until the desired number of clusters is achieved. Advantages: adaptability. Chameleon can handle clusters of varying sizes and shapes, making it more flexible than traditional methods like k-means. Second, quality of clusters. By considering both the internal structure of clusters and the relationships, Chameleon often produces higher quality clusters. In summary, Chameleon is an effective clustering method that overcomes some limitations of traditional algorithms by dynamically adapting to the data. Finally, let's discuss the importance of evaluating clustering quality and explain two methods for assessing clustering tendency or quality. Evaluating clustering quality is crucial to ensure that the clusters formed are meaningful and useful for analysis. Poor clustering can lead to incorrect conclusions and decisions. Two methods for assessing clustering quality. First, Silhouette score. This metric measures how similar an object is to its own cluster compared to other clusters. The Silhouette score ranges from -1 to 1, where a score close to 1 indicates that the object is well clustered, while a score close to -1 suggests that it may have been assigned to wrong cluster. Second, Davis-Baldwin index. This index evaluates the average similarity ratio of each cluster with its most similar cluster. A lower Davis-Baldwin index indicates better clustering quantity, as it suggests that clusters are well separated and compact. In summary, evaluating clustering quality is essential for validating the effectiveness of clustering algorithms, and metrics like Silhouette score and Davis-Baldwin index provide valuable insights into the clustering results. So that's it for today. Thank you for joining me today on the CSE Guy. We have covered a range of topics from ensemble methods like bagging and boosting to various clustering techniques. So don't forget to like, subscribe and hit the notification bell for more content. See you next time.